Good afternoon to all our delegates and participants. Welcome to day one of RIA's Unlocking Innovation event on Routes to Zero Carbon Rail. Unlocking Innovation events are the result of a collaboration between RIA, the Railway Industry Association, Network Rail and the UK Rail Research and Innovation Network, UCRIN. This specific event has also been built in participation with the Rail Safety and Standards Board, RSSB, who are leading on the collation of research on cutting CO2 emissions in the UK rail industry. So really great to have their participation. I must also mention Trevor Bradbury of Pragmatex Consulting, who's actually put this whole event together. So RIA thanks all these partners for their support in its various forms, without which this event absolutely isn't possible. So my name is Richard Jones, and I'm part of RIA's Technical and Innovation team, and I'm chairing today's event. Today, we're going to talk about driving electrification, and we have some great presenters and interesting topics from organisations including Network Rail, Siemens, Riding Sunbeams, and Loughborough University, followed by some 5-minute presentations designed to share some really great ideas so that everyone taking part gets a wide view, not just from the large organisations, but from the SMEs as well, of what's going on and who is doing what. We'll finish up with a panel question and answer session with all the speakers. So audience, delegates, you can send in questions using the question facility on your screen. And myself and colleagues will be picking up on the common themes. There will be some written answers to those questions, and some will be saved through for the Q&A as well at the end. The best questions that we'll pick out will actually go through to the panel as well. We're aiming to finish by 3:30 at the latest. So let's hear from our first speaker then. Helen McAllister, who's Strategy and Planning Director of Network Rail Wales and Western, and she's looking at how rail traction decarbonisation can support net zero by 2050. So Helen, I can't see you at the moment. If you could switch your camera on, please. That's great. Helen, can I hand over to you, please?
Hi, thanks, Richard. Thank you for the introduction. My name is Helen McAllister. I'm a Strategy and Planning Director at Network Rail, and one of the really exciting pieces of work that the team and I have been doing over the past 18 months, 2 years or so, is looking at what would need to be done to the rail network in order to remove carbon emissions from traction power. So we started up a network strategy that builds on very good work that had been done by the Decarbonisation Task Force. And what that strategy set out to do was to answer the question of which of 3 traction technologies, battery, electric or hydrogen, would need to be deployed where and when on the GB rail network in order to remove diesel trains. Now, we chose those 3 technologies because they were the ones identified via the Decarbonisation Task Force work as being the ones that are sufficiently developed at the moment to be credible solutions and replacements for diesel. The way in which we have set about this is to develop a 5-case programme business case, very much in line with HM Treasury guidance, in order that it can be fully used to support the Department of Transport's decarbonisation plan that will be coming out kind of later this year, early next year. Also, so that we could fully examine the strategic financial management elements of decarbonisation, as well as the purely economic side of things, which is the one that many people tend to be very focused on. We have already published the interim programme business case for this work that you can find on the Network Rail website. And that sets out which of these technologies would need to be deployed where, and what the strategic case for that is, and what the economics of that looks like. The when they should be deployed and the programme behind that is the subject of the full programme business case, which is due to be complete at the end of this month, which now doesn't seem very far away at all. So kind of moving on from that, the strategic case for decarbonisation has six core themes that you can see here. So obviously there is the very upfront one that says we're removing carbon emissions, and it will help You know, it helps the railway contribute towards the UK decarbonisation legislative requirements, it helps surface transport, and it helps the UK overall move towards net zero carbon by 2050, as it needs to. There can also be modal shift benefits through decarbonisation, and the traditional benefits that are associated with electrification projects of reduced journey times and reduced overall kind of long life maintenance and OPEX savings. There are further environmental benefits from air quality, largely that will be taken in rural areas, as we would fully expect any air quality issues within major cities to need to be addressed before the timescales of decarbonisation. And there's the wider economic benefits that are associated with decarbonisation. The London and the South East is already significantly an electric railway, therefore interventions that would need to happen will largely not be in London and the South East. So it is a natural levelling up of the economy. So that's kind of the strong strategic case for decarb. One of the other questions is why act now? You know, we don't need to reduce our carbon emissions fully until 2050. That's quite a long time away. Well, we need to start now in order to have any chance of getting there by 2050 in a way that is efficient and affordable. There are other sectors of the economy that are expected to not be able to achieve zero carbon emissions, and that therefore all sectors that can will need to get as close as they are able to zero in order for the UK to have a chance of netting off the residual carbon emissions across the economy. And that will be a decision best taken at a national level rather than a sector level. Traction decarbonisation will also require long-term planning, development and delivery. It's not something that can be delivered overnight. And we also need to start putting the kind of proof of concept vehicles, the battery and the hydrogen vehicles that have been demonstrated across the network into operational use in anger, so we can learn how they work, learn how to use them, learn how to run a railway on a technology source that's not electric or diesel. And hopefully that will switch down again. So the way in which we set about doing this was to take a look at those three technologies and say, what is it that they can deliver? So first off, there was a kind of technology sift, and largely due to power density, you know, electrics go anywhere. As long as you've put the wires up, it's reasonably expensive to put those wires up, but once you've got them, you can run pretty much any trains off them. Hydrogen is good at kind of up to 75 miles, 100 miles per hour ish over medium range, so 200 miles ish, accepting that both of those will increase as technology develops. And battery is best for short hops at low speeds, and where that gets you is where you have a high speed, long distance network, where you have significant freight usage of the network. That electrification is the technology answer that exists at the moment if we're going to keep all the other levels of outputs the same. So if we're going to keep journey times the same, number of stops the same, number of changes the same, then it's electrification that we need to deploy in those areas. Below that, you get much better ability to make a choice between hydrogen and battery, and there's more competition for technology. When we did that sift, that showed that straight off there's 11,500 STKs of the rail network that would need to be electrified in order to decarbonise. 400 STKs of battery, 900 of hydrogen, and 2,300 where there's no clear choice. You could, you know, there's a number of options. We then did a further additional assessment looking from a more operational perspective of, okay, you could use any technology, but which one would make more sense from a rolling stock perspective, from the characteristics of that particular piece of network, and from the bits of the network that it joins in with. And that left us, essentially, you can see the numbers along the bottom, but we got down to only 260 STKs with no clear choice at this stage from the strategy. We also came up with a number of other recommendations that I'm assuming these slides will be available after the event, so you don't have to strain your eyes now, but they are around the ways in which we need to look at the network if we're serious about decarbonising it. So, for example, any proposed new railway should consider if it's going to be able to operate in a zero carbon environment. So should it have passive provision for electrification at this stage? Should we be considering battery rolling stock for short hops? We should only now look at procuring diesel-only trains where there's a really clear economic and strategic case to do so. So rather than be a default, they need to be a, well, really why? And we might need to. There might be a good case to do it, but we just need to do that knowingly. Battery and hydrogen train operations need to start in anger, if you like, so that we can really test this technology in an operational railway, see how we run a timetable, see what the standards look like, see what the performance regime and maintenance regimes need to look like. There's a lot of stuff to work out to introduce new technologies onto the UK rail network, and the sooner we start that, the better. And overall, a stable and efficient programme of electrification is one which will give you a better value for money of doing decarbonisation. Even though value for money is not the overall aim, decarbonisation itself is the overall aim, it helps our case a lot better if we can do it in an efficient and affordable manner, especially in the economic circumstances that we find ourselves in at the moment. So they're kind of further broad recommendations. As I go down from that, this sets out now the kind of decision tree analysis that we undertook. So as I said, we did the technology focus, we looked at what the service impacts were. We then went on to the economic modelling, and we looked at 5 different pathways. So if you wanted to reduce emissions by 90%, by 85%, what would you do where? How far would you go with introducing new rolling stock and electrification? If you wanted to get to zero carbon by 2040, what would that programme look like? What's the economic case for that look like? If you want to do it by 2050, what does that look like? And if you want to look at a slightly longer time frame to try and maximise your deliverability, what does that look like? And we found that, you know, the cases that have the best economic or that show the best net value for money are those that take longer but go further. So really pushing down towards that zero carbon, but trying to take it out to 2050 and maybe a little bit beyond in order to get best value for money of how you spend that money. What we're now going to do, or what we're now in the process of doing, is redefining that delivery programme in conjunction with the Network Rail regions, the kind of rolling stock companies, and crucially the supply chain, to understand that we have a programme to put forward that is deliverable, that is efficient, to really try and avoid the boom and bust of previous cycles of electrification, to show that we can deliver efficiently in line with kind of other major economies in Europe especially. And we'll then be refreshing the economic modelling to look at 2 more pathways. So that's our new programme that we will have consulted with the supply chain and the regions to 2050, and then one that looks longer, and adding in air quality benefits as well. And that should be done by the end of the month. So following on from that, the programme business case, we've painted the end state of what the network would need to look like to support traction decarbonisation of today's services. What's really important is the when and the how of how we would get there. So we are aligning schemes to programmes, broad programmes. They're associated with kind of the carbon budget dates, and we need to keep engaging on the development and the delivery of this. We need to do it. I'm going to keep banging on about this. We need to do it in an efficient and affordable fashion, otherwise it won't get done at all. When we did the economic modelling, we have used a range of costs for the introduction of hydrogen, battery and electrification. And when you look at the top end, if you look at the top end of costs, if it's going to cost, and we're being ambitious with those costs, then you do get a negative net present value to decarbonise the railway. If you look at the bottom end of those costs, if we're really ambitious about what we can deliver in line with other countries and in line with lessons learned work that has been done by RIA, by Network Rail, by other organisations, then you can actually have a positive net present value of decarbonising the economy, even using the current tag tag guidelines and analysis, which you would expect would kind of under-egg the benefits, because it's not set up to deal with things like climate change. So one of the crucial things for a credible programme that will get us to where we need to be in terms of decarbonisation is demonstration that we can deliver efficiently, and we can deliver reliably. And I think some of the things that we'll hear, from what I can see from the other presenters across today's session and later in the week, will really set us up to deliver this successfully. So thank you very much.
Brilliant job, Helen. Thank you very much indeed. That was a beautifully clear presentation and a very clear set of slides, which really pushes us off, I think, in the right direction here. You know, this is an issue that we, despite the fact that the rail industry is by far from the worst CO2 polluter, even within transportation, it's still an issue we have to deal with, and we've got to deal with it seriously. And I think you've demonstrated very capably there that we're actually doing that. So great, thank you very much. It's really good to see this kind of work now being with engineers that are putting real numbers around it and so on. Now, just an information thing here, from the panel on the side of your screen, apart from asking questions, you can also download all the handouts as well. You'll get an email in just a little over 24 hours from GoToMeeting, which is the platform we're using, which will offer you a free download of the entire event. And within the next week or so, all of the slides and the recordings will appear on the RIA website in the innovation community. If you're a member, well, you should already have a log on. If you're not a member, you don't have to be in order to access the innovation community. Like this event is free and open to all. We want the industry to move forward with innovation, and we want the best people working in the industry, which is why, one of the reasons why we do these events. Now, there's been a really serious claim from assorted politicians over time that electrification is just too expensive to do. RIA's technical director, David Clark, has compiled the Electrification Cost Challenge report, which very much challenges that idea. And now we're going to hear from another industry champion for electrification, Justin Moss, who's the Strategic Development Director for Siemens Mobility, about how we can reduce the cost of electrification. So, Justin, can I hand over to you?
Thank you, Richard, and yeah, it was good to hear Helen's presentation a minute ago, which hopefully will touch on some of those points as well. So, good afternoon, everyone. So, following on from DfT's publishing of Decarbonisation Transport paper, electrification is set to have a major impact on decarbonising the railway. With the predominance of Victorian infrastructure, we need to overcome major engineering and cost challenges using innovation products and design of the system. The UK's investment in clean, sustainable power generation means that rail remains the most effective and efficient mode of transport for high capacity commuter, high speed, intercity and heavy freight services, with 42% of the UK's rail network now being electrified, with over 80% of vehicle kilometres travelling by electrified trains. However, that leaves 58% of the network not yet electrified, and with these routes running diesel powered rolling stock, there clearly needs to be a focus on how we can support the government's objective of phasing out diesel-only trains by 2040, and so further decarbonise the network. High-performance rail electrification is a core component in delivering end-to-end networks, digital infrastructure, and as an industry, we're striving to drive down the costs of projects while continuing to deliver operational passenger benefits. And when we're assessing new schemes, it's important that we consider the full range of options on the basis of a robust whole system, whole life assessment, ensuring the right balance is struck between long life infrastructure investment and complex rolling stock to deliver the best possible economic and environmental benefits. In March 2020, the Department of Transport published a Decarbonisation Transport paper outlining the role the transport sector has to play in achieving the government's target of net zero greenhouse gases emissions by 2050. And the paper marks the start of a process which will see the government set out the policies and plans needed to address transport emissions and to release a broad range of benefits that Decarbonise will deliver, improving people's health, creating better places to live and travel in, and driving a clean economic growth. It also recognises that electrifying of more railway will be necessary to achieve this, with major projects including the Great Western Main Line, Transpennine and Midland Main Line upgrade programmes already set to greatly expand the electrified railway network. And as an example, on the East Coast Main Line, just by replacing what was diesel trains by electric, we reckon a circa 154 tonnes of carbon dioxide emissions per day have been removed from the transport sector, simply by removing diesel rolling stock on East Coast Main Line, or equivalent of planting over 2,300 trees every day. So the railway should be considered as a system end-to-end rather than separate discrete disciplines. This will deliver the most cost-effective and efficient system. Procuring each discipline separately risks an over-specified system, as each party seeks to ensure that a part delivers the required remit, and trade-offs between different disciplines become challenging, and often a gold-plated system is delivered. So ensuring that the technology providers are involved at the early stages of feasibility in an early contractor involvement scenario on a whole route rather than small sections, so the most optimum solution can be considered. Early GRIP 3.4 modelling enables strategic shaping of electric landscape. This enables the use of digitally derived static frequency converters, the number of substations required to provide sufficient volt and amps to reliably operate electric trains and trams. And as an example, we've seen cost savings using various technologies such as static frequency converters against ATs by about 60%. The integration strategy and technology, and for controlling and powering trains in the future, will be better identified on early programmes in order to be able to model passenger flow, train location, power loading and efficient infrastructure placement. The use of air-insulated UK-built switchgear, static frequency converters, lightweight solutions in OLE such as SICAT, and solutions such as surge arresters all contribute to an efficient traction decarbonisation programme. However, as an innovative company, we're always looking to seeking to continue with optimum solutions. This can only be realised with a steady long-term procurement programme. We're really supportive. Just make sure that's. Too happy on the slides. We're fully supportive of a rolling programme of electrification. However, we need to ensure it's procured in a regular, consistent manner to avoid gaps. It should be more focused on output specifications to enable designers and manufacturers to focus on optimum delivery. Open performance specifications, but not prescriptive on the means or solutions. We also need to look at this programme as a whole system rather than procuring in piecemeal. We need to see a rolling electrification programme underwritten by government and protected, with yearly milestones against Network Rail to ensure it's procured. It needs to be consistent with a delivery level plan to avoid peaks and troughs in demand and output. Consistency provides investment confidence. Output-based specifications should be used more, i.e. we need an electrification system that will permit X number of trains to run in a given time between points X and Y. The detail of this is achieved should be left to the delivery party. Consideration should be given to procuring both together. A contractor could then balance the needs of both disciplines and propose the most efficient system for the route, and could be better manage the risks. Funding could be added to this, and we could look at the new version of market-led proposals, assuming government could resolve its approach on the off-balance sheet question. For delivering electrification, frameworks for tracking decarbonisation with reward structures for efficiencies, collaboration, and with the appropriate risk allocation between customers and contractors. Technology will evolve, and this needs to be built into programmes, so innovative and new commercial models could be employed, encouraging technology providers to offer licensings and paid on performance reliability schemes. Reducing the cost of overhead line, I saw a question earlier on. The industry has already seen benefits that new electrification technologies can bring, which are enabling significant improvements in business case for upgrades to be demonstrated. An example is development of new lightweight catenary systems, which enable significant cost and carbon savings to be made across the life of the project. With longer span lengths between structures and fewer components needed, as well as less concrete and fewer site deliveries, the overall electrification project costs greatly reduce. Together with the carbon savings it delivers, technologies like this brings real opportunity to accelerate the electrification of more of the network. Electrification, though, is clearly not the only answer to meet the government's net zero challenge. and every part of the industry has an important role to play in bringing forward new technologies and new approaches to drive efficiencies and reduce emissions, whether that be through lighter weight vehicles and hydrogen-powered trains. Electrification, though, is recognised as a crucial element of the jigsaw, and as such, the industry continues to work closely and collaboratively across the supply chain to drive down costs and deliver improved performance benefits for operators and passengers. Reducing the cost of electrical clearances. The issue has arisen when negotiating structures such as bridges and tunnels has been the need to provide sufficient electrical clearance. Clearances are defined by standards and legislation and are an essential factor when designing and developing overhead line systems. If adequate electrical clearance cannot be provided, then scheme designers have to consider whether to modify or renew the bridge or tunnel, or alternatively lower the track running through it. In response to this, we've looked at an engineering solution such as surge arresters that work on a 25 kV network in circuit with the overhead line system. It enables reduced electrical clearances to be applied and delivers significant cost and delivery benefits. By introducing surge arresters into the electrification system at bridges and tunnels, if overvoltages do occur, for example, through a lightning strike, the surge arrestor reduces the impact by magnitudes of voltage, which complies with the required electrical clearance values between overhead line and structure. Depending on the required protection level, surge arresters can be applied to the overhead line equipment by both sides of the structure and for each contact system running through it, which reduces electrical clearance. On completion of extensive test trials in 2017, our surge arresters were used and approved by Network Rail and have now been designed and installed in the UK. And since December 19, with the first installation being in Cardiff, where restrictions caused by the proximity of a canal combined with a rail intersection bridge meant that the track could not be raised or lowered to accommodate compliant electrification equipment. It's my final slide, putting my other hat on for Northern Rail industry leaders, which I co-chair. I'd really like to highlight that we are looking at our low carbon work stream, which is an output from the white paper we released last year. And the team has been working really hard in identifying key routes that need to be electrified and which other routes could work with alternative methods such as battery, hydrogen or hybrid. We're just finalising the paper ready for submission to the industry to help with the identification and review the Northern Powerhouse Rail proposals. I'm really excited what the team have produced, and I can't wait to share it, and hopefully it should be out in the next couple of weeks. So if you have any questions or like to discuss anything further what I've discussed today with our working and lobby on Northern Rail industry leaders, please get in touch. And that's it from me, Richard.
Super. Thank you very much, Justin. That's very professionally to the minute there as well. And great to see the call for levelling up on electrification, if nothing else. So that's a pretty good one. Thank you very much. Again, as before, you can ask questions in text on the screen now, and we'll have a Q&A panel right at the end of the session. So certainly a couple of other points there, Justin. We fully support the principle of looking at the railway as a complete system, and also early contractor involvement, absolutely key to getting projects right and not making some of the mistakes of the past. Now, outside the rail industry, we see an increasing uptake of renewable energy all around us. Wind turbines and solar seem to be everywhere. But where are we in rail? Alex Byford is Chief Technology Officer of Riding Sunbeams, and he knows more than most about what's actually been done today and what's planned next. And he's going to share us what he knows about these new approaches to electrification. So, Alex, can I hand over to you, please?
Yeah, thank you, Richard. Yeah, so my name is Alex Byford, and I'm Chief Technology Officer at Riding Sunbeams. So, Riding Sunbeams, we were founded by climate change charity Possible and Community Energy South. And over the past few years, we've been looking primarily at the southern routes on how we can integrate direct wire renewable generation to actually power the traction demand of the trains. One of the key elements of our work is we're looking at doing this with direct wires, community-owned generation, and doing it at a commercial price, so no need for any subsidies. And it essentially is cost neutral with Network Rail, because any money they spend on buying electricity is offset by the lack of electricity they'd be buying from the normal providers. Last year, we actually built and commissioned our first site in Aldershot. It's a small 40 kilowatt, it's a small 40 kilowatt proof of concept and it's actually currently powering the trains as we speak. You might be wondering why we should be looking at these two industries. So the renewables industry and the rail industry are actually a match made in heaven. You've got a customer that uses huge amounts of electricity every year, has strict targets on decarbonisation, has a fantastic credit rating, and has a reason to stay in situ. So large factories and things can end up moving for various reasons, but the railways will be staying put. This coupled with it's quite difficult now to actually connect renewables to the grid because of the grid constraints. There's already a lot of constraints on the transmission network and the distribution networks. So the work we did with the Rail Safety and Standards Board was called Green Valley Lines, and we undertook a feasibility study looking at the electrification of the core valley lines on Transport for Wales network and seeing if we could integrate renewables, direct wire renewables into this at the design stage. So principally, we had a look at a few work streams. We tried to assess what the suitable engineering solutions were for connecting renewables indirectly, the actual scope for finding sites, available sites along those routes, and then the market conditions that would allow this to be commercially viable. So back to basics, there are two significant types of electrification in the UK at the moment. About a third of the network is third rail 750 volt DC, as you can see on the left. On the right hand side, that's the AC network, 25 kV AC, and that's generally used on the faster lines north of the River Thames. Principally, our work had focused on the DC routes and how we could connect in there, and we've got a technical solution for that. But looking at the Green Valley lines and the lines in Wales, they're powering with 25 kV AC. So we had to look at adjusting our method. So the first element of this is physically, how would you actually connect into the network? It's actually simpler than it might seem. You could use a fairly standard piece of equipment, a gantry. You would then, next to the network, have a small compound which would have a joint access switch, circuit breaker, similar equipment to that. You then have a 1 or 2 kilometre private wire that would take you to the remote site, which would be where your wind or solar generation is. And the benefit of this principle means you can get the economies of scale of large solar or wind sites, but minimise the amount of work on the traction network. You'd only have to do a very small amount of work to install the gantry. So the physical method of connection is relatively straightforward, but the first hurdle is what I call the Goldilocks issue. So with the AC networks, they run on a single phase electricity at very high current ratings, which is fairly unusual in the renewables industry. So typically, single phase electricity is only used in domestic installations. So if you had solar panels on your house, you might have a single phase inverter. And then at the other end of the scale, you have the utility scale items, that static frequency converters, which were mentioned earlier. They are around £1 million a megawatt and start at a sort of minimum sizing of about 12 megawatts. So you end up having a choice between the domestic, which you need hundreds of them to work, and they probably wouldn't stand the duty cycle of the railway, or a huge, massive static frequency converter, which would completely ruin the financials of the project. So we found that we needed a low-cost modular converter. And the good news about this is that technology largely already exists. Most trains have a traction converter already, which is how they are powered by the overhead wires, and they tend to be bidirectional, that they can also send current back through regenerative braking. So our plan is to repurpose some hardware similar to that to actually make this low-cost modular converter. One of the key elements of delivering direct wire to the network is around understanding the systems level and the systems breakdown of the network. So principally, they're divided into electrical sections, and those electrical sections will have different demand characteristics. So you need to understand on a second-by-second basis what the kind of base load currents there are. This becomes more complicated now with bi- and tri-mode trains. We have both regenerative braking and energy storage. And then you also need to add on to this the capacity of the wires and and also the timetables of the trains themselves. So we looked principally at solar and wind, and they're both excellent in terms of their characteristics for use with powering the rail network, and they're obviously widely used now on the grid system. But the key differences are around the generation characteristics, and you have to try and match those generation characteristics with the demand levels of the railway. So with solar power, you tend to get a peak during the middle of the day, which can be when you would have a lower level of train service compared to the peaks in the morning and the evenings. And then the challenge with wind is that it generates 24/7. So you could end up with wind powering in the evenings with no trains, and you'd need to do something with this electricity. The less attractive option is curtailment, which is where you would essentially ramp it down or turn it off. But the most attractive option is to actually export this additional power back by the grid supply point. There are obviously regulatory and technical challenges to that, but from a systems level point of view, this will allow far more of the traction power to be decarbonised, and that is without any subsidies, so this would still be at a commercial basis. The other element of this is looking at land availability and planning considerations. With solar, you obviously need large amounts of land at the right quality and likely to get through planning permission. And then wind, there's been some challenges of onshore wind to actually be able to get planning permission in the first place. We looked at energy storage. One of the key findings was on a co-location basis, so simply adding a battery to a solar site and connecting it in, or to a wind site, it tended to harm the business case at this point with the capex costs as they are. But where we found there's a real opportunity is looking at it over the whole electrical sections, where over a large electrical section, it could be 10 to 20 kilometers, you might end up with different load profiles and different generators connected. You might have both wind and solar, and this is where having a battery on the network can really help boost the economic viability of the project through load shifting. If the batteries could provide services to the national grid, they'd almost certainly have an attractive economic case, because that is currently what's used in the market. But there are technical challenges of being able to commit to those markets when you're sat behind Rail's distribution network, especially with how it can be reconfigured and other technical challenges. The key element obviously is to make sure there are enough sites to provide the load. So we followed a standard method in the renewables industry, looking along the railway lines within 1 to 2 kilometres at possible available sites. The headline figure is that we found about 33% more viable sites than we needed, which is important because a lot of sites won't necessarily get through the planning process and may not have the technical suitability or a motivated seller. Going back to the systems level view requirement, bringing all these elements together means it really needs strong interaction with the owner of the assets to understand exactly where you need to put the generation. We thought it might be easier doing this at the design stage, but there's a strong argument, say retrofitting could be slightly easier, because you can actually take second by second data logging data and understand exactly what the generation profiles, so the demand profiles of the train vehicles are likely to be. We also looked at supporting an islanded depot. So the last 6 miles of one of the lines, the trains are going to run on batteries due to challenges in electrifying them with overhead conductors. We principally looked at supplying about 40% of the load required, but we're now looking at the possibility of actually aiding with the electrification itself, so that a smaller grid connection is required, because the location of that depot, which is going to have a stabling load of trains overnight, is actually in quite a difficult place to get a large grid connection. So the key findings, essentially we found about 40% of the total traction demand across these lines could be supplied by line-side wind and solar, and that would be at a price that's commercially attractive and would be in line or cheaper than what would be paid for with a normal grid connection. We found well over the number of sites that we needed, which is a strong case to say that you would actually be able to meet that demand with the resources available. But then we found that the converter cost is really critical for the viability of this. Because there's no suitable converter at a viable price point at the moment, one will have to be developed to enable this idea. And the final one is that we need to be able to export to the grid from the rail grid supply points. If you can't get paid for the excess power that you're generating, it really does harm the economies of the projects, and you would need some form of subsidy then to make them viable. So the next steps for us on the back of this, we're currently working on our 4 megawatt solar project in East Sussex, connected to the DC routes, and hope to be commissioned by March 2022. We're undertaking the converter development ourselves to enable the ability to connect to the AC routes, and we're planning a demonstration of this technology on the Great Western Main Line with Network Rail. So thank you very much. I look forward to answering any questions later on.
Thank you so much, Alex. That's intriguing. I didn't know enough about what you were doing. I knew you were working on the Green Valleys project, so really, really exciting stuff, and great to see people actually digging into this to figure out what's going to work and what's not going to work. These things always start with a good economic assessment, but as soon as they come to the engineering, sometimes things grind to a halt. And terrific that you've highlighted this gap in the market around a medium-size static frequency converter, if you like.
Yeah.
Super, that's really good. So thank you again, Alex. Thank you very much indeed. So on to our next speaker. Bi-mode trains have been with us for quite a while now, and they are certainly already contributing to decreased emissions. But are the contributions optimal? Sometimes when something is a good thing, we don't always stop and say, yeah, but is it the best it could possibly be? Dr. Tim Harrison of Loughborough University has been researching this area, and he's going to share his work with us on optimal power control. So, Tim, can I hand over to you, please?
Thanks, Richard, for the introduction. I'm Tim Harrison of Loughborough University, and I've been working on this with a colleague who's Dr. Will Midgley, and this has been supported by RSSB. So we're going to have some aims and objectives for our little project. So we aim to build and validate a model to simulate fuel consumption and CO2 emissions of a bi-mode train. Of course, we need a bi-mode train to base this on, and at the time we started the project, the most numerous example around were the Class 800 type trains from Hitachi. We then tended to compare the emissions from the bi-mode train to pure diesel train and see what difference that makes, and then to design a controller to try and reduce the CO2 produced by the bi-mode train. The model we built, this computer model, looks a bit like this. The power flows up the middle, so we have the overhead line equipment at the bottom through transformer, rectifier to a DC bus, the auxiliary power supply off that for brake compressors, doors, whatever else that might be, inverter to the electric motor, and the influences come in from the side. So on the left side we've got speed limits and timetable, which the driver takes notice of, the torque speed characteristics of the train, how that works. On the right hand side we've got the gradient, wind, all those effects through the train and the gearbox. And that could be considered a conventional electric train. If you then add into that diesel engine and generator, then you have your bi-mode train. And something we've looked at as a kind of an add-on to this project is what happens if you add in some sort of energy storage on the side, be it a battery or whatever that might look like, and you get some sort of high tri-mode or hybrid train, whatever you want to call that. The way we looked at influencing the control of the train, we have a number of controllable modules in there, if you like. That's how we can influence how this thing performs. So once you've built a model, it's a good idea to validate it so that you know the numbers coming out at the end make some sort of sense. So we went for a day riding trains, and we picked a particular diagram that starts ends at North Pole Depot in West London, and the train on that day, it does 2 return trips, one from Paddington to Paignton and then out from Paddington to Plymouth. The gradient profile over the line looks something like that, up to about 150 meters above sea level over the 350 odd kilometers it is from London to Plymouth. We went on that particular day, it was 802.006, which is a 5-car train set. And we logged accelerations in 3 axes, all the rotational accelerations and the GPS. The accelerations are there just so that we can make sure we have the data we need through tunnels and when the GPS signal is not available. So the data we get looks something like this. The red line is from the train on the day, and the blue line is what our model does. This is a London to Plymouth run. You can see that we've quite nicely matched the acceleration rates and deceleration rates. The train, broadly, though, they match. There are a few little cases where the train was significantly slower than line speed, but that's signal checks or the trains influencing how the driver's driving. If you plot that against distance from London, we can now put in the speed limit, and you can see that we're broadly a 100-mile-an-hour railway through across the route. There's a section at 125 at the beginning out from London, and towards the end it's at 60 miles an hour. So what do we find in terms of carbon emissions? So we've got the Paddington to Paignton, Paddington to Plymouth routes there. Also, we've modelled Paddington to Swansea and King's Cross to York. As of 2019, the routes out of Paddington towards Plymouth are about a quarter electrified as far as Newbury. In 2019, the Paddington to Swansea line was only electrified as far as Bristol Parkway, which is about 60% of the route, because King's Cross to York's been 100% electrified for some time. In terms of the carbon emission, when running on the overhead, then the carbon emission tends to increase a little bit. So it starts around about 13 and goes up to about 14 grams of CO2 per passenger kilometre, and that's mainly due to it's a pure energy use thing. So the carbon emission goes up with the power you're using, and you're using greater power to run at higher speeds. When in diesel mode, it actually runs the other way a little bit, and that's because you have reduced efficiency when you're running at part throttle with the diesel engine. So with those slower routes, then we've got a slightly greater carbon emission. The next column over is the 2019 mix. So if you do the part of the route under diesel and part of the route under electric traction, then that gives you the grams of CO2 per passenger kilometre for that route. The possible CO2 reduction is how much you would reduce the carbon emission if you electrified the complete route. So currently Paddington to Plymouth route, we've got about a quarter of it's electrified. If you then electrify all the way out to Plymouth, then you'll get a 66% reduction in carbon emission. Moving on to our optimization part, we looked at the Paddington to Plymouth route with the current overhead infrastructure, so that's electrified out to Newbury and then diesel beyond. We varied a number of control parameters up to the point at which we impact on the timetable. So we didn't assume we could have any easing of the timetable. And there's a number of parameters we looked at to try and reduce the energy use and CO2 emission of the train without impacting on its performance. Those 6 are across the top there. You can see, so the current demand rate limit is effectively like the driver using the power control a little more gently. Doesn't give you a great deal of CO2 reduction. Control gain is effectively like driving a heavier train. It's kind of a power limit. Now, this gives quite a big reduction in CO2s for when using on electric mode, but that's because the train's power in electric mode is limited by the traction package, the electric traction package, and we assume we can draw the current we need from the overhead. It doesn't have such a great impact in diesel mode because the train's performances are limited by the power of the diesel engines in that case. Throttle rate limit is how the control system opens up the diesel engine throttle in response to a power demand. Generator power limit is just the power that the generator can produce, and we have a couple of other factors there. the target deceleration rate there is reduces the deceleration rate of the train into the station. So the reduction comes from reducing the amount of time the train is at cruise power before we begin to break into the stations. So we were slightly disappointed that we couldn't get some greater reductions here, but it looks like you can get about just over 3% reduction in carbon emission by using some of these sort of control interventions. So beyond this, we've tried to look at some other means of reducing the carbon emissions of the trains. Something that has come up and has been used on the UK network on some other train classes is selective engine shutdown. So this is something we can do in a model quite easily. At lower speeds, the engines run at part throttle because you're not using the full power required of them. So it's actually more efficient to turn off one or two of the engines when that full power is not required and use the remaining engines at a higher power setting. So again, this was tested over the Paddington to Plymouth route, and we think you can get about an 8% reduction in CO2 emission just by powering down engines that are idling or running at low power over the route. But the stop-start produces additional engine wear, starter motor wear, so there's that trade-off between that emissions reduction and the engine life reduction or the overhaul costs you might incur on the diesel engines and generator sets. The next thing we looked at is to try and use the time that's available in the timetable. So if the model accelerates away from the stations up to line speed, cruises at line speed, then brakes into the station, generally arrives early because there's that little bit of slack built into the timetable. So this controller looks forward at the speed limits ahead and where the next station stop is and predicts the arrival time at the next station. If that arrival time is predicted to be early, then the cruising speed over that section is reduced. Doing this, we can get about 10% reduction in CO2 emissions. It's easy to integrate into current driver advisory systems. To a certain extent, this is what some of them may already be doing. And we could also use this to inform driver education tools. The obvious question is, can you combine those two things? And yes, you can. And it looks a little like that. So you have on the bar chart to the right, we have some of the control measures we tried, a relatively low improvement in carbon dioxide emissions. Then the selective engine shutdown and the predicting the arrival time. And if you combine those two, we can get about 19% reduction in CO2 emission. But they're not purely additive because there are non-linearities, particularly in the way the engine and the generator set work. And those percentages will change depending on the route. So the nature of the route, the gradients, station stops, and also the electrification ratio on any given route. Speaking of electrification ratio, we looked into, this is a little piece of work we did with the TD&S people at Network Rail. We looked into how the CO2 emissions changed based on partial electrification of a route. So we have here percentage of the route electrified across the bottom. At the left, 0% of the route electrified. We run entirely on diesel, and it's about 42 grams of CO2 per passenger kilometre. On the other hand, if we were to electrify the entire route, we have about 12 grams of CO2 per passenger kilometre, and you can see the mix we have in between. It's not entirely linear. There is a little bit of variation there depending on the nature of the route between the stations. Something we did try to do was an intermittent electrification. So what happens if we electrify only the parts of the route where the trains are operating at high power? So whilst the trains are accelerating, whilst they're decelerating on the hills, they're drawing a high power. So if you work out which parts of the line the trains draw high power, that's about 40% of the route. That's in and out of the stations, up and down the hills, those sections. The remaining 60%, the trains are generally cruising and they're not using a great deal of power. So if you do that 40% is the yellow diamond there, you see. And so we can, if we electrify 40% of the route, that intermittent 40%, we can get that CO2 per passenger kilometre down to about 25 grams per kilometre. Interestingly then, with the Class 802s and their 3 engines, of course, if you're running on electric mode in the high power sections while they're accelerating or going up and down the hills, then you actually only need 2 engines on the train to maintain the cruising sections of the part. So we can drop that down to where the blue square is there. Those CO2 emissions, the reductions, if you baseline that to where we are today, Paddington to Newbury electrified, you can see we've already reduced by about 18% the carbon emissions by doing that electrification. If you were to extend the wires out to Castle Carey, you'd get to about 3/4 of the emissions of today's the current state, 2/3 with Paddington to Taunton, about half if you took the wires to Exeter, and you'd get down to about 1/3 of the carbon emissions taking the wires all the way out to Plymouth. So in conclusion, we've got a model that runs the timetable and can be adapted to match the speed and time data. The controller optimization that we set out to do reveals about just over 3% reduction in CO2 emissions. We can get almost 20% by mixing in selective engine shutdown and looking ahead and predicting your arrival time. And we have a useful tool for quickly investigating the effects of various electrification scenarios, whether that's partial electrification or intermittent electrification. Where we'd like to take this now, one of our the other projects that the RSSB supported was from Newcastle University. They looked at co-simulations and functional mock-up interface for decarbonisation projects, and looked at a driver model, which is something our model doesn't have a particularly detailed driver model. There are obvious synergies there, so we think that the next step, and we're talking about this now with RSSB, is to merge those 2 projects to have a full train model, driver model, and wrapped up with functional mock-up interfaces in the first stage, and then to move that on to multiple routes and different traction types in a second and third stages. Just one remaining thing to do is to skipped over my last slide. Thanks to the RSSB for their we're going back to the last slide. For the funding of the project and the various partners that helped us out on the way.
Of course, Tim, you're welcome to do that. And it is important to acknowledge the amount of investment that RSSB has led on in this whole area of decarbonisation. So all the work that Andrew Cluth has done, which has been a cost to RSSB, it's been a phenomenal effort and a really good, strong team at RSSB that have pulled this together. And it's great to see they pulled in the right people who are prepared to ask the right questions and drill down for the information. So great. Thank you very much, Tim. Right, we're going to go for a quick change of gear now. So we're going to move into our 5-minute sessions called elevator pitches. So called because it's what you could explain about your project or your organization in an elevator in just a few minutes while it ascends a building. It's a long elevator, 5 minutes, but hey, you know. The first one is talking about enabling inefficient electrification. And it's definitely not an SME. It's Richard Stainton, who's one of the class of engineering experts at Network Rail. Now, Richard, are you just on the phone, or have we got a camera there as well?
Aye.
So if you can enable the
camera, yeah. Yep.
Great, we can see you, Richard. Are you ready to go?
Okay. Yeah, I'm ready. 5 minutes. Okay then. Right. Okay. Welcome everybody. Yeah, my name's Richard Stainton. I work in Network Rail as an electrification engineer, and this is to give a quick update on the phase 1 of our work stream on enabling efficient electrification. It's made up of 10 separate work streams, and I'll give you a highlight of a few of them. So moving further on, oops, what's going on there? Right, excellent, it's working. The first one of the work streams I actually tell you about is insulated pantograph horns. Insulated pantograph horns are not new to the UK. Sorry, are not new idea, but are new to the UK. They replace the composite, the conductive pantograph horn with a composite horn, as you can see in the photograph on the right-hand side. So the white pantograph horn is a composite, the non-conducting, And the idea is that we can retrofit the composite pantograph horns onto existing pantographs used in the UK. We've undertaken all the laboratory mechanical and electrical tests for deviation against the group standard, and we are planning to carry out in-service trials this year. This will allow us to reduce the required electrical envelope for pantographs to reduce the cost of bridges and platforms, station platforms. Moving quickly on, ice loading. So the current requirement for wire height in the group standard, and that requires us to take into account the likelihood of lightning strikes and ice accumulation occurring concurrently. This piece of work provides a justification for those two weather extremes to be assessed by OLE designers separately rather than concurrently, which reduces the clearances by about requirements by about 55 millimeters. We presented the report to RSSB, and we will include this in the next update to 1210. Further on overline design, building on the work that we carried out on Great Western Electrification project at Steventon Road Bridge, we are looking to make the OLE design rules on gradients less onerous, and we are carrying this out by modelling this year with plans to test at Old Dolby next year before we can update UKMS on the second half of 2021. We're also looking to update UKMS with the contact wire uplift requirements. We're currently carrying out measurements at 10 sites throughout the UK, or GB, to measure different contact wire uplift to take into account for pantograph types, OLE types, and different service patterns to allow us to have a much more comprehensive rule on contact wire uplift and to be much more focused in our design rule in the future, reducing another few millimeters of the requirement for electrifying underneath OLE bridges. And this all builds on the work we carried out at University of Southampton a couple of years ago for the Cardiff intersection bridge. We're actually back there at the moment. It started a few weeks ago, not next week as it says in the slide below. But we're testing all sorts of different OLE componentry, and we're also testing various bridge construction materials, including masonry and concrete, as well as steel, to really understand the minimum electrical clearance required for all the types of bridge types and OLE designs. And the intention is to include this in UKMS OLE designs in the future, and also in our Network Rail standards in the next, to be updated next year. We've not just focused on electrical clearances and bridges, we also looked at the practical installation of overline. So we've carried out some benchmarking of different OLE foundation or piling techniques. There's a photograph there of not using one technique, but two techniques simultaneously. But we've carried out a number of different benchmarking activities at 3 different sites in the UK to provide specifiers of high output plants in the future with better guidance on what piling technique works best where. Now, one of the criticisms of the OLE designs range that we have at the moment, in particular structures, is that the structures are over-engineered compared to our European counterparts. So we've carried out benchmarking with a Deutsche Bahn of our OLE structure types. So you can see on the right-hand side the UK structure from the Northwest Electrification scheme, and one that Deutsche Bahn have designed for us. And we're currently reviewing their design output. There's quite a few interesting conclusions and some challenges, not where we expect them to be. But yeah, there are certainly some room for improvement on simplification in OLE design structures. And finally, we're doing a scheme that's been called RATS for Classic. So building on the work that Great Western have done on rationalising the number of substations required for an auto transformer system, we're looking to rationalise the number of substations required for a classic electrification scheme. We're currently building this on a timetable between Perth and Aberdeen, but by March next year, we aim to have a safety case and a system specification for a rationalised classic scheme, which basically means reducing the number of substations on the scheme dramatically. I think that's my 5 minutes up. Is that the top of the escalator lift?
Got to the top in excellent form, Richard. Well done. Thank you very much indeed. Excellent job. Thank you. I'm sorry that's a short time and it's such an important topic. There we go. Probably need to stop that. Okay, good. So on to our next, please. I mentioned earlier on UKRIN, the UK Rail Research and Innovation Network. One of the key institutions there is the Institute for Railway Research at Huddersfield University. And Professor Joao Pombo is a good example of somebody who's a global expert in overhead line and pantograph interaction. So Joao is going to tell us about some of the work they're doing there. Over to you, Joao.
Thanks a lot, Richard. Thanks for the introduction. Good afternoon, everyone. So I'd like to present this short elevator pitch on the work that we are doing on Panto-LE. So just a few slides about motivation. I think what we are trying to tackle here is to improve current collection, also to avoid incidents and accidents that cause traffic disruptions, also to improve behavior and to the authorization process. And another point that we are tackling is to improve pantograph and OLE designs. So in terms of the numerical tool that we have developed and now it's certified by our network rail, what I can tell you about is that we can do all these types of studies that you can see here. So we can do authorization process, we can do multiple pantograph operation, any type of catenaries, AC normal, AC stitch catenaries, and also DC double contact wire catenaries, all the scenarios that you see here on the bottom. And I would say more importantly, we have just, in the partnership we have with Network Rail, we have just certified our tool that is called PantoCat against the new 50318 2018. You can see here that according to the standard for a software tool to be certified, it needs to be compliant with the numerical, with the test data of 80, at minimum 80%, but for instance, for the two first ones, the AC simple, high speed, and the AC stitched ones, we got around 95%, and for the double contact wire, got 90% compliance with the experimental data, which is good. And now the tool is certified for all types of catenaries, including also rigid catenaries. And another capability for a tool is that it can not only do the lumped mass model approach to study the pantographs, like you see here on your left-hand side. That is basically you need a test bench to identify a linear model that has the same frequency response as the real pantograph. But it has several drawbacks. Number one is that you need a test bench to identify the model. Number two is that the model is fully linear. So does not have non-linearities, for instance, associated to different ranges of opening of a pantograph. So we have proved already that this type of models cannot use to study gradients, for instance. And on the right-hand side, you can see another approach that our software is able to do is that we can do a fully multi-body approach. So we can model a pantograph like we model a vehicle, for instance, in Vampire, identifying all the bodies, connection elements, and suspension elements. And then you can run simulations in our numerical tool, and you will be able to do optimization studies, for instance. This is one of the reasons why Siemens came to us, Siemens Austria and German came to us, and we are now developing a project with them to develop a new conventional relay network pantograph. So our software works in a co-simulation environment. The catenary is modeled in finite elements, the pantograph is modeled in finite multi-body. And every time you talk about finite elements, you think that it took a lot of time to run, but I can tell you that you can run a full wire run, one section of catenary more than 1 kilometer in 5 minutes, so it's very efficient. Another thing that we can do is that we can do very long tracks. So in one European project, the Shift2Rail project that we are leading, we proved to the European Rail Agency and the Shift2Rail that if you can model more detailed catenary models like you see here, with several overlaps, curves, gradients, if you have these detailed models, then you can relax some of the criteria that are defined in the standard for the authorization process. And it's one of the key areas that the European Rail Agency is keen for us to propose simplified methods to simplify the authorization process. We also have our rig in the scope of UKRIN, like Richard was saying. I believe that all of you know what UKRIN is, but in the scope of UKRIN, we are funding this 3.5 million test rig at the University of Huddersfield. And I can show a few details here. Unfortunately, in the handouts that you've got with you, you cannot see the videos there, but if you have any questions, just send me an email and I'll be more than happy to send these videos to you. So like I was saying, it's a full-scale pantograph rig. The pantograph sits on a motion platform that can mimic any car body movement. And on the top of it, you apply loads independently in each contact strip at speeds above 400 kilometers per hour. You can see here on the bottom on this video. And these loads are applied independently on the contact strips, mimicking the catenary. So it's hardware in the loop because half of the system is hardware, is the pantograph itself, and the other part of the complex system that we are studying here is the software, that is the catenary model that mimics the loads that the pantograph suffers when running in any situation. So you can see here, we are commissioning this rig during this month, and hopefully it'll be fully operational in November, and all of you are more than welcome to come and visit us to see more about what we are doing here. So in terms of challenges and conclusions, what we can do here with our tools, with our numerical tools and with the rig, is that we can help any electrification project. We can also support cost savings in the electrification process. We can help bi-mode tests. So for instance, one of the things, the key areas that are keen to study is to use electric bi-mode. So trains running on batteries plus pantograph OLE. So the idea is that instead of rebuilding the tunnels when doing new electrification projects, because our tunnels are from Victorian age, so there is no enough clearance to put catenaries inside them. Instead of rebuilding tunnels and bridges, why not to use batteries while running inside the tunnels, and then when you go out the tunnel, you raise the pantograph again and you run on OLE while you charge the batteries again for the next tunnel. This is one of the ideas. Another idea that we are exploring is to test new sensing systems, and from the data coming from there, we can have pattern recognitions to identify defects before they occur, and also to promote what we call predictive maintenance. So predict the maintenance features and inform the maintenance decisions of companies. So that's me. Thank you very much, Richard.
Super. The important thing there, Joe, is your contact information. The people can contact you through RIA if they can't get hold of you, jpombo@hud.ac.uk.
Yeah.
Thank you very much. That was a 2-hour presentation delivered not in your first language in 5 minutes. Well, 16.
Okay. Thanks, Richard. Thank you.
I wish I could do any of those things, actually. Right. So to our last presenter before the Q&A, obviously what you all came for, heavy metal versus light rock. So I'm very pleased to hand you over to Steve Barber, MD of Composite Braiding Limited. Steve.
Well, thank you very much, Richard. Very much appreciate the introduction and the opportunity to speak to you today. The conversation or the presentation is entitled Heavy Rock versus Light Rail. I'm going to talk to you today about some innovations in material options for rail, which isn't so much this, it's more this. In particular, in this particular case, we have a structural pole designed to replace a steel one. It's 16 kilos versus over 80 that can be made from volcanic rock and be non-conductive, but I'm getting ahead of myself. I'm describing today a journey that we're currently on. This presentation is intended to make you aware of some genuinely new developments. If you think you've heard all about advanced composites and think this may be a great time to go make a cup of tea, I ask that you give me the next couple of minutes to update you on some new and exciting options. This really is different. These options can be used on their own or with existing materials. Right material, right place, it's always going to be correct. Please ask yourself at the end of this presentation, could we potentially build back better with help of some of these materials? In fact, to take Helen's point earlier, can we also make it more efficient and more affordable? I give some examples on this chart of potential rail infrastructure options, but you'll understand your market needs better than me. We understand the technology. Let's see how we can help you. But don't just take my word that we have a new exciting set of material options. Our technology has won 2 global innovation awards in rail. Global Light Rail Innovation of the Year for rolling stock in October of last year, and JEC Rail Vehicle and Infrastructure Innovation in May of this. For those of you not in the composites industry, JEC is the Oscars of the composites sector, and our peer group thankfully judged this development as being worthy of recognition. Other category winners elsewhere included the likes of Volkswagen, who were somewhat daunted by the company we were keeping. The innovation is based around braiding. For those of you not familiar with that process, it's a way of weaving tubular structures very quickly. Indeed, we've already shown that we can braid at rates of over a mile a day because it's highly automated. We significantly reduce labour costs and make it much more affordable. We then consolidate the material into a component. We're developing the ability to do that in just minutes, making much higher volumes available and again saving cost. This quick consolidation process works for smaller components right up to structural columns of up to 6 meters in length, and we produce much less waste, most of which is reusable. The quick processing, greatly reduced labour and huge reduction in waste makes the products more affordable than traditional composite manufacturing routes. We have a proper industrial process. Finally, because we use thermoplastic matrices, we can bend, join and shape components in ways that you can't with metal or other types of composite materials. We can even weld them. There are a range of materials available, but all involve a combination of fibre and a matrix. By using this breadth of materials, we gain an excellent mix of properties. On the fibre side, we have the usual composite options, carbon, glass and aramid, the latter of which includes things like Kevlar. But we also have basalt, which, yes, is volcanic rock and has good sustainability credentials, as well as being even more electrically insulative than glass. We're also starting to work on thermoplastics that have additional features, including bio-derived and those that give us other properties. In one of our programs, we're developing materials for high contact surfaces that will provide permanent antimicrobial properties. As I've said, this range of materials gives us a great deal of design freedom, which in turn allows us to offer an array of benefits. Some examples are shown on this chart. I don't have time to run through each of them now, but with your knowledge of your applications and any issues you may face, we'll be happy to explore with you where we can add value and explore which benefits would apply. Your applications could see our technology being a replacement for the materials you use now or in combination with them. We understand our technology, you know your needs. Let's discuss how we can help each other. We are also developing components and capabilities for other aspects of rail, but we'll save the details for that for another day. However, as you'll see, the materials and processes that we use give us a wide array of product types. So I hope I've conveyed that we offer state-of-the-art developments in lightweighting technology that can help you decarbonise the railways. I asked the question near the start, could you potentially build back better with the help of some of these materials? I hope I've given you some food for thought. We'll be happy to engage with you and help you determine where and how we could add value to you and your customers. I also hope that you think that missing out on that cup of tea was worth it. Thank you, and here are my contact details.
Thank you.
Deep off, Richard.
Here's one I made earlier. Thanks for saying blue, Peter. Excellent. Well, there's your time up. Fantastic. Brilliant job. Thank you so much indeed. And I completely concur with everything you said there, Steve. There's real innovation in materials out there in industry, and we so need to be using these things in rail. Right, lots of the questions are almost around, I guess, policy and strategy, but it's quite good to get a feel from the panel. So if you could all please bring your cameras and microphones back up. You spoke earlier, would you come back and join me? So cameras and microphones. So Jenny Cook, a colleague of yours at Network Rail, Helen, so question I think aimed at you, but open to other opinions. And East West Rail, it's proposed currently not to use electrification on East West Rail. It seems illogical. Jenny says short-sighted. What do you think, Helen?
I think that projects and programs that are in development at the moment have got a really difficult job to do because they have a set of outputs that they need to deliver and funding proposals that they need to deliver them to against quite a changing backdrop of requirements. So we don't know yet the extent of decarbonisation of traction power that will be required in the UK to help deliver 2050. We've got to look at it alongside what you need from roads, what you need from air, what you need from all the other economic sectors. So it's not a nailed-on certainty that you'll need to have an electric, hydrogen or battery east-west rail, let alone which of those technologies is the absolutely correct answer. So I've got a lot of sympathy with them that they need to keep delivering their programme. We have shared our work with them, so they know what our workings look like and what we think. We've shared our work with the Department for Transport, so they know what our work looks like and what we think. It will be included and inform the transport decarbonisation plan. I think they're taking a really pragmatic look on East-West Rail at what they can do to minimise any future costs of decarbonising that bit of network. It's really difficult, and it plays into the West Midlands question that came later on as well about the DMU trains that were ordered there. Decisions are going to have to be made every day in order for us to keep delivering improvements to the railway network that are being made on the basis of incomplete knowledge. No one has certainty about what we need to deliver. So I think we just need to recognise that when we're looking at some of the different projects that are being delivered.
Yeah, thank you, Helen. Yeah, I understand it's difficult, but we have among the audience a journalist, so somebody who's a professional communicator, David Shiras from Rail Engineer magazine, and he's essentially asking, are we really advising decision makers on the right options? In this case, electric trains versus self-powered trains. Do we feel that we're doing all we can as an industry to advise decision makers, so DFT and ministers as well, I guess, on what the right options are? Helen, you might want to address that first of all.
Yes, so I think that if you need a zero carbon rail network in 2050, then absolutely you would need to have a different option to diesel on East-West Rail. And you might notice that there's a lot of ifs in that statement, because we don't know yet what we can advise what the railway would need to do. What the railway can't do is make the trade-offs of decisions about what needs to be done on different parts of the economy. Decarbonising the overall economy is a huge task, and going to be hugely expensive, and there is much constrained money. And until government have a better idea of how much it is going to cost and what the actions that are required to decarbonise different economic sectors, it's not possible to say what the right answer for rail is, let alone kind of make a decision that will add a lot of money, I would have thought, because I haven't seen any numbers on East-West Rail, a lot of money onto the cost of a project when you don't know that it's necessary, if you can look at how you minimise the impact of that for the future. So we need to give the best advice to government that we can, but then government need to make the decisions about how far and how fast the rail industry goes on decarbonisation.
Thank you, Helen. Justin, you're someone who voluntarily gives your time to be part of the joint Northern Rail Industry Leaders Group. How are you finding engagement with DFT and with politicians in terms of pushing electrification?
I mean, certainly it's something we're talking about as a whole, but I think it's not just talking around electrification and sort of like the carbon benefits of it, but it's when we're looking at other systems like hydrogen and batteries, it's considering the whole scope, because obviously you've got with hydrogen you still have to manufacture it, and we haven't really got that sort of green manufacturing yet. With batteries you still got that sort of life of a battery which needs to replace. So at the moment electrification is the one system that we actually understand and know how to operate. So certainly I think the challenge the government are having is, yes, they'd like to electrify everything as main routes as possible, but they recognise that it's not the biggest thing that's making the carbon problem. There's other transport systems that are, and obviously if you've got funding decisions to make, then they're going to look at the biggest net benefits first, aren't they?
Okay, so big politics plays into this, and a wider cause than just decarbonisation of rail. So Question for Alex Byford of Riding Sunbeams. You mentioned land quality for solar. What are the quality features or barriers to installation of solar about the land? Probably 3 years ago, I spent a bit of time with a renewable energy company you may be familiar with, Ecotricity, and they told me that there was enough land on and around the railway to power the entire UK railway in terms of solar and wind turbines. Is it the right quality of land though? What determines that?
Yeah, you have the typical land quality issues that you would have with any kind of solar or wind installation. So straight away, you're looking at the resource availability. You know, how much sun, for example, for solar, and the wind for wind. You've got the agricultural quality of the land. Too high value land, you don't want to be necessarily taken up with renewables. Obviously, land contamination, access issues. Shading for solar, if you've got trees and things like that on the land, that's all very important. Flood risks. These are kind of the standard parts of renewable development. But when it comes to the railway, the biggest challenge, the obvious one, is being close to the railway, but it's also being at the right connection point. So with the AC networks, you can pretty much connect anywhere along the overhead wires, but you have to take into account the systems point of view and really understand where the demand's needed. And then essentially, once you've mapped where the demand is needed and the characteristics of that, you can start overlaying what the supply elements are of the renewable resource. And it's marrying the two things up that makes it particularly difficult for rail use rather than typically as you would just connect to the DNO.
Okay, thank you. We need to sort of make sure that we understand those barriers and when we're in a position to deal with them. Again, it's just joined up thinking, isn't it? And it's great to have this group of people. They're all working on parts of the solution. And, we really need to be encouraged to work together to really get there.
Just on the land quality, it's less about land quality issues and it's much more about power purchase agreements with the rail industry. That's the thing that's really going to drive it, and it can happen very rapidly. Once that framework is out there, the land issues are really the least of the worries.
Okay, yeah, absolutely. I think the 10-year agreement comes up in 2022, something like that. So there needs to be some quick decisions made if we're going to change from just doing 10-year fixed purchase agreements with the big utilities. So question for Tim. It's a technicality, I guess, around startup and go offline time for engines on bi-mode trains. Are you calculating around those, and do engine startup and shutdown times make your calculations meaningless?
We're not putting in any meaningful startup time at the moment. We'd made the assumption that I know there are extended startup times, but we've kind of assumed that those are first-time startup times at the beginning or the end of the day. So if the engine's already hot, it's already warm, some of the auxiliaries could already be running, then startup time shouldn't be 10 minutes for a diesel engine. My car does it in seconds, and it's not that much of a bigger engine. So yes, there are startup times, and I know there are concerns over greater wear on the engines, those sort of things. But if you design from those in from the beginning, then I'm sure we can get those times down to a few seconds. We did study how sensitive the on-off switching is, as it were. So you can make it incredibly sensitive. So as soon as you back off the power, the engine's shut down, and you can have the engine starting and stopping hundreds of times over a journey, or you can make it less sensitive, and you have only a handful of startup and stop cycles, but of course that's less efficient because it takes longer to shut down and longer to start up. We looked at the trade-off there.
Okay, and a quick question, which can go first of all to Richard Stainton. When you're looking at OLE structures, have you addressed their frangibility in the event of a derailment when compared with the German designs?
We haven't, no, not yet. We both follow the EN 50119, which doesn't have any specific frangibility requirements, but yeah, something to look at in the future.
And do you think perhaps Steve Barber's composite OLE structures could be an answer there.
I think that's one of the opportunities for phase 2 is looking at different structure materials for sure. So yes.
Brilliant. Okay. Super. I'm going to say thank you very much, everybody. Really delighted with the set of presentations today. So thanks to all of our presenters, thanks to all of our delegates, thanks to all my colleagues as well who've been peddling away in the background to make this work. It's Hannah and Milda and Trevor, and to Trevor again for the preparation on this event. Great job. So thank you all very much indeed, and I hope we see you soon. Carry on the good work. Thank you.
Thank you.
Bye.
Bye.
Thank you very much.
Bye.